In this set of class notes, what we're going to do is take what we learned in the video notes, which was looking at exponential functions and their graphs and things like that, and we're going to apply that to some more real-world type situations. So exponential functions model a lot of real-world phenomena, and so we're going to look at some of those in this set of notes. So starting by taking a look at example 1, it says that a culture starts with 8,600 bacteria. After 2 hours, the count is 12,400. Now it wants us to find a function of the form n of t equals a times b to the t that models the number of bacteria as a function of hours. All right, so remember one thing about this equation is that a is the initial value, right? So we know that a in our case has to be that 8,600 that we started off with, right? The initial amount. So we already know that, so we can, maybe write this down. N of t is equal to 8,600 times b to the t. So what we need to do is find what b is. What is the base in order to be able to state what this function is explicitly? But of course what we have here, this is similar to when you had to find the equation of a line, right? In the application, there really is another ordered pair that they've given us, right? So what's the ordered pair? Well, it's saying after 2 hours, the population's up to 12,400, right? It's an ordered pair, and so what can I do? I can stick that in. So 12,400 goes in for the function value, and 2 goes in for t. But of course now our only unknown is our b. So if I want to solve for b, I would start by dividing both sides by 8,600. And I'm not really too worried about getting this thing simplified, so I'm just going to be a little bit lazier about it. And so where I'm at right now is I'm just going to say that this is, I know it's not reduced, but that's okay. This is equal to b squared. Okay. But of course, how do I solve something like b squared equals a number? We know that we're going to take the square root. So this is going to be the square root of 12,400 over 8,600. Now, if you're thinking right now, do we need plus or minus? That's good, because you're thinking about the algebraically correct thing to do is when we take the square root of both sides, we'd have to say plus or minus the square root. But remember that the base of an exponent can never be negative, right? It's always going to be positive in every case. So that's why I'm just simply saying that it's equal to the square root. And then, so what I have is approximately 1.2008, okay, is what our b translates to. And so what I guess I should kind of update this. So our function, right, as a final answer is this, 8,600, 1.2008 raised to the t power. And remember our discussion back in the video notes about you can write an exponential function as b to the t, or you can think of it as 1 plus r raised to the t. So this you could think of as 1 plus 0.2008. And so remember that this amount that you're adding is the growth rate of about 20% per hour, right? That's the idea here, is that gives you the percentage growth or decay rate, depending on if it's plus or minus. So that's what the meaning of that is. All right, but at any rate, let's answer the question. It says find the number of bacteria after 3 hours. So n of 3 is equal to 8,600, 1.2008 to the third, and that gives us about 14,890 bacteria, and that seems pretty reasonable based on how we started and where we were after 2 hours. I'm pretty happy with that answer. Okay, so one thing I do want to point out here, though, is that it would have been a little bit better if I had not rounded this base. So what I did is I kept a lot of decimal places, but the very best thing to do, of course, would be to keep it in this exact form and plop that in there. I did it this way because I wanted to point out this relationship between the growth rate and the b-value. But just note that it's always better to leave things exact when you can, or if you're not going to do that, like I did, make sure you keep a lot of decimal places. All right, so now let's take a look at example 2. This one says that suppose that a person invests $2,000 in an account that earns 3% per year. How much money will the person have in 5 years? Okay, so we want to come up with this. Maybe I'll call it A of T, right? So this is T in years. Okay, so let's kind of work on the same type of thing that we did in the last one, but in this case, they tell us how much the account earns, right? Or how much it grows by. So when you're thinking about this, I would think about it from the standpoint of y equals A times 1 plus r to the t, right? As opposed to b to the t. So the reason I think about it this way is because, well, 2,000 is going to be our A, so I can put that in there. But if it's growing by 3%, the way you can think about it is I'm starting with my full amount, 100% of my amount, and I'm adding 3% each year. So I raise that to the t power. So just to clean that up, A of t equals 2,000, 1.03 to the t power. And so therefore A of 5 after 5 years gives us our answer, so about $2,318.55. Right? Now, if you're thinking about investments, 3% is a pretty modest growth. That would be like what you're going to get out of a really safe investment that has a little risk involved. And so what is this saying? It's saying if you let your money sit in that account for 5 years, you end up making $318.55 just by letting it sit there. Okay. All right, let's go to the next page here and talk a little bit more about investing money. So you can have situations where every year you grow by a certain percentage, like in this one. But often in the world of finance, when you have an account, it actually compounds interest more often. Okay, and so this is referred to as compound interest. So I think the best way to approach this is I'm just going to give us the formula, talk about what the pieces mean, and then when we have that example number 3 in front of us, we can kind of digest it a little bit easier and kind of dig into why it is that the formula actually makes a lot of sense. All right, so what do we have? Well, A is the initial amount, right? The starting amount in the account. T is measured in years. This is always measured in years, by the way, when we're talking about compound interest. R is the annual percentage rate, also called the nominal rate that the account is growing by. Okay, and you can also say that if it's like a loan, like how much money you owe as well. That's another way this can be applied. And then K is the number of compounding periods in 1 year. So in 1 year, how many times essentially are they calculating the interest? Okay. How much are they calculating the interest? Okay, so let's apply it to this problem, and then we'll kind of dig into this formula a little bit more. So we're given that. So how much money is in an account that earns 4.2% annual interest, compounded quarterly if $500 was invested 7 years ago? So we have all these numbers they're throwing at us, right? So let's write down the function first. A of t is equal to, well, do we know little a? Do we know the initial amount? Well, yes, because we know we invested $500. That's what we're starting off with. Okay. The number 1 is always right here. Okay, and then R. Well, we know R, right? The annual interest, right? Annual interest is the annual percentage rate. Same thing, just slightly different language. Okay, but of course my R value is not going to be 4.2. It is going to be the decimal form of that percentage, so 0.042. And then we're compounding quarterly. So the K is equal to 4. So I put a 4 down there, but then I also put a 4 up here in the exponent, right? So you put the compounding in both of these places, and then you put your T here. So there's my formula. And I can answer this question. Let me answer the question first, and then we'll kind of talk more about this formula. So A of 7 would be 500 times 1 plus 0.042 over 4 raised to the 4 times 7. Okay, and so of course we need to multiply that exponent first. The 28th, and then probably go ahead and put that in our calculator now, and what we get is $669.86. All right, so there's our answer. Okay, but let's dig into this a little bit more. Why does this formula make some sense? So what I would have us do here is, let's see. Actually, I'm going to do it up here so that I can more easily compare it to that formula. So let's do this. Let's invest $500 for 1 year, okay, just to see how this works. If you did it for 1 year, of course, that would be 500 times 1 plus 0.042 over 4 raised to the 4 times 1, right? But let's break down what this means. If we're raising this thing to the 4th, it's literally 500 times that times itself times itself times itself, right? Okay, so here's what we're saying. After 3 months have passed, take a quarter of the total percentage that the APR is and apply that after 3 months, right? And then after 6 months, right, after 2 quarters of the year have passed, go ahead and multiply by this one, which will indicate more growth, but you only get to grow not by the entire 4.2%, but by a quarter of it. And then after 9 months, do it again, and then finally do it one last time at the end of 12 months. So we're splitting that APR up into 4 equal parts, but we are calculating the interest at each stage, okay? Now, what's interesting, though, about this is it matters, okay? If you get to apply portions of your interest earlier on in the process, then by the time 6 months comes around, not only are you earning the interest on the $500, but you're also earning it on the little bit of extra money that you made here, okay? And then after 9 months, you get to earn interest on the 6 month, the 3 month, and the 500, right? So compound interest does make a difference. You make more money the more times a year you compound your interest. All right, let's do another example where we're going to use this formula. And you do need to memorize this formula. This won't be one that I will give to you. But what I want you to just think about here is you've already talked about and know this one, right? Right? We know that. Okay? So all we're suggesting here is that you replace x with t because it's going to represent time. And because you're compounding your interest multiple times a year, instead of just saying 1 plus r, you're going to say 1 plus r over k and then put a k here. So basically, you're just taking this formula, but just adding the k here and here. And that's all. So it is one I do want you to have memorized. So what's happening in number 4 here? Suppose a mother wants to be able to buy her son a used car on his 18th birthday. She figures the type of car he wants to buy, she wants to buy him will be about $8,000 at that time. She wants to invest money now that will grow to that amount when the time comes. So she invests the money in an account that has a 3.1% annual percentage rate that compounds monthly. If he is currently 10 years old, how much money must he invest now? All right, so first of all, let's come up with our function. So a of t, notice they did not tell us what the initial amount is. They're telling this 8,000 is what she's going to need to spend eventually. So we don't know a, but we do know the interest rate, 3.1%, and it's compounded monthly, it says. So that would be 12 times a year to the 12t. Now, what is this 8,000? Well, this 8,000 is what she wants to end up with at the end of 8 years, right? So the 8,000 goes in for the amount. We still don't know how much she invested. That's what they're asking us for. And then up here, it's 8, so we'll put just an 8 right there. So this is 8,000 equals a 1 plus 0.031 to the 96th power. So this might look a little bit ugly, but we got to remember that this thing here is just a number. Okay, it's a complicated looking number, but it's just a number. So in order to figure out what a is, all we have to do is divide by it. And this one, even though it's a lot to type in, if you just literally type this in, 8,000 divided by parentheses 1 plus all this, and then raised to 96th, you don't have to do anything fancy in your calculator. The order of operations will just take care of it. And what your calculator ends up spitting out to you here is $6,244.88. And that is about what she should be putting in the account now so that the money is ready for her when she needs it. All right, so this business that we talked about of the fact that compounding more often is better. All right, let's discuss that a little bit. So which is better, to invest at 4.1% APR compounded daily or at 4.2% compounded annually? All right, now if I wanted to answer this question, what we could do is let's invest. How about we do it this way? Invest $8 for 1 year in each of those accounts and see what happens. Okay, so $8 for 1 year at 4.1% compounded daily would be, plugging a 1 in there, a times, and it'd be 1 plus 0.041 over 365 to the 365 times 1. And if I calculated this thing, I would get A times 1.0418. So what do we know? That we know that it grew by 4.18% because I take 1 away from that to get the growth rate. Okay. Well, 4.2% compounded annually is a little bit better than that. Okay, so we would say that 4.2% compounded annually is better in this case. But it was close, right? This one had, for all practical purposes, a growth rate of 4.18% after a year, even though it reported a 4.1% annual percentage rate. So you can see how compounding more often gives you a higher, and the term we use for this is annual percentage yield. What does it actually yield after a year? Okay, so let's just understand how we got this number. Let me just write it out in this manner. We took 1 plus 0.041 over 365 that was raised to the 365, and we took 1 away from it, right? And that gave us the 0.0418. So on the next page here, that's this formula. So the annual percentage yield is just basically plugging 1 in for the time, 1 in for the investment, and then subtracting 1 off, and that'll always give you your annual percentage yield. Okay, and so if you're ever asked which of these two investment scenarios is a better one, that's what you want to go with. All right, so we have this idea that things get better and better the more times we compound during a year or whatever the time period of interest is. So a natural question would be, what happens if I just keep compounding more and more often? All right. So to kind of explore this question, what we're going to do is we're going to invest $1 at 100% APR for 1 year, and that's just to make things look a lot or be a lot easier on us. Okay, and so here in the table we're just keeping track of how many times we're compounding. Here we're putting in what the formula looks like with these numbers plugged in the appropriate places, and then how much you end up with at the end. So if I compound just once a year, I end up with $2, right? 100% interest means whatever you started with, you get at the end of the year. So you get a total of $2. But if you compound twice a year, you end up with $2.25. 4 times a year, you end up with $2.44, right? It keeps getting better and better. 12 months a year, $2.61. 365 days a year, $2.71. So it continues to grow. But if you notice, as you go, it grows by less and less, right? So here it's just plus 0.25. Here, what's it at? It's plus 0.19, right? Plus 0.13, plus 0.10, right? So the amount that it's getting better by decreases as I go. So the question is there a cap on this? All right. So if I was to put one last one here, k, right, where I could put any number in here, it would be 1 plus 1 over k to the k. So the question is, what happens to this in the long run when you let k get bigger and bigger? So it turns out the answer to that question is this. If you let k get really, really big, then what happens is it does not just get as big as you want, it settles down to a particular number. It settles down to this number e. And so this number e is about 2.718, okay? And it is, think of it like the number pi. It's this really special number that comes out when you allow this compounding of interest to occur more and more often. Okay. All right, so how do we apply this? So the next page, it gives us a new formula for if you compound your interest continuously. Okay. Now you might wonder, why are we talking about compounding interest continuously? No bank ever does that, right? And that's true. No bank ever does that in a literal sense. They never, like, they're not actually having computers continuously compounding interest. However, there are plenty of places where this is applicable. Okay, I'm going to come back up here to this part. Let's skip down to example 6 so you can see how this is applicable. So what are they saying? I'm going to have to take that off the screen. So they're saying, here's the formula you should be using. Okay, so in example 6 here, it says, suppose that the inflation rate for continuous compounding is 3%. If it costs a family an average of $48,000 per year to live in 2010, how much will it cost in the year 2015 or the year 2050? So inflation is this concept that the value of money changes over time, right? So what you could buy with $1 in 1960 is very different than what you can buy with $1 today. All right, and this idea of inflation is something that we think of more as changing continuously, because it's not like every so often during the year someone's deciding that money is worth, it has different value than it did before. It's not like there's this regular interval. It's just kind of continuously happening. So this type of formula is much more appropriate. All right, so what's the formula? F of x equals 48,000 e to the 0.03x. Okay, so if they say, okay, in 2015, what would it cost? Because x is years since 2010. So in 2015, that would mean that 5 years have passed, right? So I can go ahead and plug that in. And that kicks out $55,000, 768 cents, or $768.04. So, what does this mean practically? If this is what's happening with inflation, then at a very minimum, if I have a job that pays me $48,000 in 2010, I would hope that that job, at the very least, gives me a raise up to $55,768 5 years from then, right? So it's not like I'm even at this point, if that was the inflation rate for those 3 years, it's not even like I'm getting a raise if they give me this much, really, because it can buy the same amount of stuff my $48,000 could buy in 2010. Let's look at 2050. And it's kind of funny. 2010 was when I began my career, so I picked the number 2050. About 40 years of work before you retire, right? So, so if I put 40 in there, if we start at 48,000, then what does that turn into after 40 years? So what that turns into is $159,365.61. So what that means is if you are living comfortably at your $40,000 salary now, when you think about retirement, you better not be thinking about how do I continue to bring in $48,000 a year. You have to think about, when I retire, how do I bring in $160,000 a year? Because that is going to be the amount of money required for a similar standard of living to $48,000 now. Okay, so when you're thinking about that kind of thing, it's important to keep inflation in mind. Now, I will say inflation in recent history has not been 3%. It's been less than that. It's been more like 2% during normal economic times. But this gives you kind of an idea of the type of thing you got to think about. All right, so what about this formula? This is strange, and let me tell you what's really strange about this formula. If you go back to that previous page, sorry, 2 pages ago, or maybe 3 pages ago, there we go, r is in the base of the exponent. Now, all of a sudden, magically, r is up in the exponent. So I just wanted to kind of justify this for you. This isn't something that I'll ever ask you to do from, on a test or anything like that. But this is just kind of cool little trick to explain why this formula occurs. So what if we compounded k times per year and we started with this formula, 1 plus r over k, the kx. Okay, so basically the compound interest formula. So what I'm going to do is I'm just going to make a clever little substitution here. So I'm just going to introduce a new letter. So I'm going to say that n is equal to k divided by r. And so that also means that 1 over n equals r divided by k. So I've just kind of flip-flop those. And so what that means is that my r over k can become 1 over n. Okay, but then that also means if I, cross these, that k equals nr, right? And so that allows me to substitute this out as well. So here's what I have. All right, so here's my new formula. But we also know, because of our exponent rules, that turns into a, and so what I can do is I can take this n that's being multiplied by this r, and I can turn it into a power raised to a power. So I'm going to bring this n in here, and then have the rx out here, right? This is equivalent to this based on our exponent rules. But now here's what we're going to do. The whole point of this was we want to let k get big, right? That's what we did on that previous page. So let k get really, really big. Let it go to infinity. Okay? If k goes to infinity, then n also has to go to infinity because r is just, a constant number. So then we let n go to infinity as well. But if n goes to infinity, what we learned on the previous page is that this turns into e. So that's where the function a e to the rx comes from. So just kind of a fun little proof of why this formula makes sense. Again, I would never ask you to do this on a test, but I think it's... So let's do one last example here. It says the population of a certain species of fish has a continuous growth rate of 1.2% per year. It is estimated that the population in 2010 was 12 million. All right, now it's very reasonable to think about population growth in terms of a continuous growth rate. And depending on the species, it may be really close to reality or maybe not so much, right? So if you think about something like salmon that swim, go from the ocean, swim up the river, and go spawn at a particular time of year, then of course, basically all the new generation is kind of coming up all at once, as opposed to continuously throughout the year. However, as a general matter, continuous growth rates are a good way of talking about population. So we're going to use the continuous model for fish in this example. All right, so write an equation gives the population in millions t years after 2010. So just a wording thing here. When they ask for the population in millions, that means that they want the equation to spit out a number that we will then multiply by 1 million. So if the equation spits out 5, I know that that really means 5 million, okay? And then of course, t years after 2010, we would say t equals 0 in 2010, right? Okay, so it's a continuous growth rate, so we know we have to use E. It was 12 million in 2010, so that's what it was initially. So my population would have an initial value of 12, and then we are taking that as e to the 0.012 times t, right? And where's that 0.012 coming from? That's coming from the 1.2% per year. So I kind of regret now my choice in numbers, right? 12, 1.2, but these are completely separate things, right? This is coming from the 12 million, and this is coming from the 1.2%. All right, so there's our equation. Then it says estimate the fish population in the year 2015. Okay, great, we can do that. So in 2015, we can plug that in, and we get about 12.74, okay? But we remember that when it spits out 12.74, what it really means is 12.74 million fish, right? So when they say in millions, we got to remember to make sure that that label gets on there. And then finally, it asks us to graph this function in the graphing calculator over an appropriate window, and it asks, should we use this equation to estimate the population of the fish species in the year 2100? All right, so let's get that thing graphed first. So in my y equals menu, I will be, so we'll type in 12 e raised to 0.012 times x. Now let's think about the window here, right? This is going to spit out numbers like 12 million and larger. So we definitely don't want any negative y values, so let's make that 0. And for a maximum y value, right, yes, we're talking about millions, but it's going to spit out just pretty small numbers that we then multiply by a million. So I'm not sure exactly. Let's type in 100 right now, okay? See what happens. And then for the x, we're starting in the year 2010. They're asking us about the year 2100, so that's 90 years away. So maybe we'll just go from 0 to 100 and see what that looks like. Okay, so that's what I see here. And if I go back here, I'm kind of thinking that perhaps my my y scale doesn't need to be quite so large. So maybe let's change this to 50. Then I might be able to get a better look. There we go. Okay. So they're asking, should I continue to use this in the year 2100? And to answer that question, we want to know when x is 90, what's the value? On your calculator, you can find that really easy by using the trace button. So if you hit trace, then you can just type in 90 for the x value, and it will take you right there. And it's saying 35.3 million. So what do we think about that? Well, that would be triple the number of fish we started with, right? Approximately triple the number of fish we started with. So the answer to that really depends upon the fish's ecosystem and whether it can support that many fish. And so it's very likely that if a fish population started to grow along this curve, there would be factors that would push that population back down, right? So anytime you're talking about population growth, what'll end up happening is you have things like scarcity of food. Also, if there's more of a population, predators will have a much easier time, capturing prey and things like that. So what we have to understand is that we have to be careful about using a model too far into the future when it comes to population growth. And so it very well could be the case that that by the time you hit 2100, using such a model is not realistic anymore. And in fact, when it comes to population growth, pure exponential growth can model populations over short intervals at times, but really never can over the long term.